Good morning, grade 9s. Today we're going to talk about scale diagrams and reductions. Now, yesterday's lesson 7.1, I introduced a little bit of the reduction to you so you could understand the difference between an enlargement and a reduction. But we're going to focus more on the reductions today. So let's just talk about where you would use these things, right? Where would scale diagrams be used in which there are enlargements? Well, in manufacturing, you have to give a very accurate drawing of what you're trying to build. And sometimes some of the objects are very small that you want to manufacture. So what you would do is you would make a drawing of that, but you would make it larger so people could see the features of that little tiny thing. Because if you drew it as its original size, say it's a 1 centimeter by 1 centimeter object, it's too hard to see, what the actual features are. But if you took that 1 centimeter by 1 centimeter object and you made it, a page size, and you could show everybody exactly what was there. Okay? The other thing you could do is you could enlarge a photograph. You could take something which is small and you could have it printed up in a larger format. Now, reductions are always when you want to take something very, very large and fit it on a piece of paper. So what that means is, a lot of times this is done in architecture. You'll take a drawing of a house, or you take a drawing of something you're going to build, which is very, very large, and you would reduce it down so that it would fit on your paper. Blueprints are what we normally call building for a house. Okay, so let's take a look at an example here. The following page is a map from Google Earth that shows the south side of the petroleum site in Hardisty, Alberta. How would a scale factor be useful? So let's just pop over and take a look at this. This is the aerial view of just part of the Hardisty plant. And what would this be useful for? Well, you can see here that here's your huts, here's your house, I should say, the buildings down here. You get an idea how big they are compared to the size of the tanks. Something like this could be used to show people that you actually have put what's called a protection around the tank, so it ever, breaks or something, that oil would be contained inside here. Right? And you can see that they've got some done here, but some here that they're still working on. This site is under construction right now. All right. Now, the other thing you could do is, if you wanted to fence something, you can't see it very well, but there's there's a big hill here, and if you wanted to fence this off, you could use this diagram with the scale to figure out how much fencing you need, rather than going out there with a very long meter stick and trying to measure it manually. You could use this in the scale, and you could say, okay, how long is this? How long is that? How long is this? That would be helpful. Right? You can also use it for laying out plans if you wanted to put something. So, for example, you can see right here, they've got a place here for another of the tanks, and here's a partially built one, and they're going to be putting the top on this soon, and then they're going to probably try and build another one right there. So it can be used for planning too. So how are we going to figure out stuff with this? So you could use, let's say, how would a scale factor be useful on the page below? Well, you could use it to make maps, calculate distances, find the lengths of fences, to enclose a facility, and stuff like that. So what we need to do is we need to calculate the scale factor. Now, I'll tell you, because I know that the line on this diagram right here, the distance from here all the way across to here is 880 meters. It's quite a ways. All right. Now, so what I need you to do is, if I know this is 880 and that's the real one, right? And so I know my real one's 880. How long is that diagram right there? So going forward, I can grab my ruler, and you can see that if I take and put that right there, there it is. Okay, so you can see that this is going up to almost right there. So we're talking about that's a 0.5, 0.6, 0.7, 0.75, somewhere around there. Okay, so from our measurement, we know that the diagram's measurement is 7.75, and I'm going to round to 7.7, right? And then, of course, the bottom one I told you was 880 meters, and I've already done the conversion here for you. So let's just show you how I did that. We know we had 880 meters. To convert 880 meters to centimeters, we know that there's 100 centimeters in 1 meter. Now, if you think about this as a big, your fraction calculations, top times top, bottom times bottom, right? We know that, so this should say centimeters, doesn't look very well, okay? We know that the meters on the top and the meters on the bottom are going to cancel out, so that leaves me with 880 times the 100. Of course, that gives me 88000. So that's my 88,000, which you see right here. Okay, now 7.7 centimeters divided by 88,000 centimeters is equal to 0.0000875. Okay, and the reason it's so small is that we're taking a very large area and compressing it down to be a very small drawing on a page. Okay, now you'll notice also that the centimeters here cancel. All right, because there's 888,000 centimeters on the original diagram, and there's 7.7 centimeters in the drawing, and centimeters over centimeters cancel, and they have to, because in scale factors we do not have any units. This is our ratio. Okay, now what I want to do is, I'm not going to actually do much for this one. We'll do something with the other one, but I want to simplify this. Now, in all ratios, and I don't know why I've got a centimeter there, but in all ratios, it's always 1 to something. That's the ratio that we want to have. Now, I'm not talking about a scale factor. I'm talking about a ratio here. All right. So you take a look at this, 7.788,000. In order to get this to be a 1, I got to divide 7.7 by 7.7. But whatever I do to one side, I have to do to the other, just like an equation. So 7.7 divided by 7.7 gives me 1, and 88,000 divided by 7.7 gives me 11,429, and of course I rounded that off. Okay, so what this means is that 1 unit on the map is equal to 11,429 units on the ground. So if you measure 5 centimeters on the map, this is equal to 5 times 11,429, or 57,145 centimeters. Of course, divide by 100 means you get 571 meters. So you could go back to this drawing and you could start making all sorts of drawings and measurements. And you could measure from here to here, you could measure from here to here, here to here, and you want to close that all off. Well, you could measure all of these and just multiply them of 11,429, and then divide it by 100, and you'd have the exact distance that you would need. So for calculating the distance around the outside here, maybe you want to fence this off, that's very simple to do. Right? You could also measure whatever else you wanted to do on this diagram. It really doesn't matter, because you could measure whatever you wanted, and you could actually find out what that distance is. Okay, this is a drafting of a cabin. And this would be what we would call a reduction. Now, it's a reduction because we've taken the real object, which is the cabin, and we've reduced it down to be on a piece of paper. So, using the drawing dimensions shown, from this wall to that wall is 12 meters, and from this wall to that wall is 5 meters. I want you to find out what the scale factor is. So, we know this is supposed to be 12 meters. How long is this on a diagram? Well, if you take a look, get your big ruler out. All right, here's my big ruler. Okay, now I have a problem here because my ruler is too short. All right, it doesn't quite get to where it's supposed to. But I'll tell you right now that this here from there to there is 15.8 centimeters. All right, so if I know that, the next step is to figure out what it is in real life. Of course, that's 12. Now remember, this is in meters. So now to get my scale factor, remember we have to get the units to be the same so they'll cancel out. So the 15.8 centimeters, we're not going to touch that, but I have to change the 12 meters into a centimeters. Now to do that, I need to know how many centimeters are in a meter. And I know there's 100 centimeters in 1 meter. Now, you remember what I showed you before, where we had sort of like a drawing here, I put fractions on fractions, and you had like a 1 here? And then top times top and bottom times bottom. The meters up here will cancel with the meters down here. So what I'm left with is 12 times 100, or 1,200 centimeters, because the centimeters are the only thing left. So I've now got 15.8 centimeters in the top and 1,200 centimeters in the bottom. Of course, these now will cancel. 15.8 divided by 1,200 gives us 0.01316666 repeating. And of course, I'm going to round this off and keep 4 digits. And there you go. You see the dot above that equal sign? That means this has been rounded, right? Now that I have the scale factor, I can answer questions about how big things are inside this drawing here. So what is the length of the coffee table? Well, the length of the coffee table, you got to go back here and you got to find a ruler and you're going to have to measure the coffee table, right? So you could take a look right there and you can see that this coffee table is roughly, what, 2.65, I think it works out to be. Okay, so there's your drawing, 2.65 centimeters. My original is unknown. We don't know what the original is. That's what we're trying to figure out. But we do know our scale factor is 0.01317. Now to solve this, what we're going to do is we're going to set up a proportional problem. Now a proportional problem is just one that's got two fractions equal to each other. So there's a proportional problem. Now, we've talked about this before. If you want to get the x on the top, which makes it very easy, there's what we can do is just flip it. But whatever you do to one side, you have to do to... Okay, so here's my flip. Numerator became the denominator became the numerator. Now, because I did both things equally on each side, there's no change in its actual values. So now that I've got this, I can solve this. How do you get rid of the 2.65 centimeters in the denominator? Well, you multiply this, the whole fraction, by 2.65, and the x over 2.65, these will now cancel out, because 2.65 divided by 2.65 is 1, and the centimeters also cancel. So that leaves me with x on the right side, and that's what I want. But whatever I do to the right side, I've got to do to the left side too. So here's the fraction that was there. I've got to multiply this by 2.65 centimeters. Okay. Now, when I do that, this is what I end up getting. I get 201.21488823, and this is ellipsis, means it goes on forever, dot, dot, dot. It's in centimeters. And then when I round it off, I round it off to 2 decimal places. So the coffee table is 201.21 centimeters long. Now, does that seem reasonable? Well, some coffee tables are very long and some are not so long. But a 6-foot coffee table, or that's what this would roughly be, 201 centimeters, is very reasonable. So now this is what I want you to do. I want you to do the queen size bed. All right. So I want to set up, there's your scale factor. Okay. And this here is my new, and this is my original. Okay. Oh, I kind of messed up. Okay. I'll give you that. Just take and finish that question off, please. All right, just like before, if I want to get the variable in the top to make it easy to work with, I flip both sides. So this becomes 1 over 0.01317. This becomes x over 2.5 centimeters. Multiply both sides by 2.5 centimeters, and what will happen is on this side, the centimeters will cancel, and so will this 2.5 over 2.5. Anything divided by itself is 1. So that just gives us 1x, or just x. On the left-hand side, I've got 1 over 0.01317 multiplied by 2.5, and that gives you 189.8253607. Now, your measurement may not have been exactly the same as mine. Maybe you had 2.45 or you had 2.6 or something like that. It all depends on what you had, but you should be very, very close to this. So this means this is around 200 centimeters, 189.83. So we're about 190 centimeters roughly. Does this seem reasonable? Yeah. It's reasonable. It's kind of on that little, maybe on the short side, but it's actually very good. Okay, here's a large box. Now this box is going to be scaled down with a scale of 1 to 25. So we know that this is the drawing, and it's 1/25 of its original size. So how large is the original box? To do that, you have to understand what 1 to 25 means. 1 to 25 means that 1 millimeter on the drawing is equal to 25 millimeters on the box. Right? Now this is the 1 to 25. So what is the scale factor? Well, the scale factor is 1 to 25, and the drawing to the real means that the 1's on the top and the 25's on the bottom. Now you could divide this out, or you could just leave it as a fraction. So what is the length of the original box? Well, my length here is 55 millimeters on the drawing. Okay, so that means that I've got to take and figure out what 55 millimeters is after I apply a scale factor of 1/25 to it. So here's my scale factor, and I have 55 millimeters is the drawing, That's the, you know, the drawing. And here's the real, so on the bottom, that's what I'm trying to find out. How big is this? So again, same thing. We can flip both sides. Multiply both sides by 55. 55 cancels out. 25 times 55 means that the box is actually 1,375 millimeters long, or 137 centimeters long, or 1.375 meters long when you do the conversions. Okay, so what I want you to do is I want you to do the width of the box. Okay, so pause the recording, and I'd like you to finish that off, please. Okay, so same thing as before. Scale factor, scale diagram. We know it's there we go. The width of the box is given up here. It's 30. I think I made a mistake here. This is width. I was thinking this is length and width here, so I guess I'm not doing the width. I'm doing the height. It doesn't really matter. We'll do the 30, I think. All right, so this becomes flip both sides, multiply both sides, and that means we're 750 millimeters. Okay, let's go back and do the other one here so that we can, because you may not have used this. You may have used the 18.3, but that doesn't cause any difficulties because our scale factor is still going to be equal to the drawing over the real. I'm going to shorten it up. So my scale factor is going to be equal to 1 over 25, right? So that's okay. That's what we already know. Now to set this up, we know the scale factor is 125. We can put that over here, and that's equal to the real drawing, which is here, and that's 18.03 over the unknown right there. So the next step I have to do here is I've got to take and flip this over, so that becomes 25 over 1. And this here becomes x over 18.03. So I've got to multiply this by 18.03, and they will cancel out. And I'm going to multiply this by 18.03. And then getting your calculator out, you should see that 18.03 times 25 should have gotten you 450.75. So 450.75. All right. So you should have gotten the same thing I did. There's all three of them here. So if you have any difficulty, just review it again. Going on to the next page. First off, how can you tell from the scale factor if the drawing that you're making is going to be an enlargement or a reduction? Now remember, we told you that scale factor is what you multiply, right? So it's a multiplication of your drawing size. So if I use a scale factor of 1, everything being multiplied by 1, it would be a 1-to-1 ratio. It would not be an enlargement or a reduction. It would be the same. If I wanted it greater, I'd have to multiply by a number greater than 1. So scale factors greater than 1 are what we call enlargements. And of course, if I want to have it less, I want to have it half size, I have to multiply by 0.5. So that is a reduction. So here, what we're going to do is we're going to try to figure out which one of these is a scale diagram that matches A. To do that, we need to have the dimensions. So I want you to stop the recording, and I want you to fill in all the lengths and widths of those 5 diagrams. Okay, so just do it real quickly here. Okay, that is 5. I'm not going to put the centimeters in, I'm just going to do it, okay? All right, this over here, that's 4. All right, this here, that's 2.5 or 2.5. All right, and this here, that's 1.5. And this over here is 4. Okay, so now let's do the widths. This one here, right here, that's 10. This over here, that's 2. Let's go over here. That one's 1.5, and that one's 3.5. And of course, the last one we have to do is right here, and that is 2.5. Okay, so what I've done and what you've done is we've now got all the lengths and all the widths. So what I want to do is I want to set up a ratio of length to width of A and see which one of these matches it. Because if it matches the ratio, the reduced ratio, then it'll be the same thing. So let's take a look at figure A. The length is 10 and the width was 5. So when I reduce this fraction, I get 2 over 1. So what happens here is this is a 2-to-1 ratio. This length here is twice the width. Now, which other ones of these have a length which is twice the width? Now, when I give you these questions, you have to prove to me and disprove. So you can't just say, oh, it's this one. You've got to put them all down and work it out. Well, here is your figure B. It's 2.5 long and 1.5 wide. When you take and reduce that and divide it out, you get 1.666666, which is 1 2/3 over 1. C becomes this, 2 1/3 over 1. D becomes 1.6 over 1. And figure E becomes 2 over 1. So you can see right now that this one here and this one here are equal. That means figure A is equal to figure E. So figure E is the only option, or the only rectangle that has the same ratio of length to width. So that means it's proportional. Okay, so have a shot at your assignment. If you have any questions, let me know, and we'll see you in the next lesson.